Hello, and welcome to this webinar brought to you by Epoxy Technology. Epoxy Technology is part of the Meridian Adhesives Group Electronics Division. My name is Matthew, and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today. Just to the right of the main presentation window is the Speaker Bio window, with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. And now, I would like to introduce today's presenter. With us today, we have Brian Bruce, the Product Manager for Meridian Adhesive Group's Electronics Division, coming to us from Epoxy Technology. To read more about Brian, please look at the Speaker Bio window right next to the main presentation window. And Brian, welcome to today's event. And with that, I will pass things along to you to get started.
Good afternoon, everybody. Thank you for joining me. Today, Epoxy Technology presents optimized epoxy dispensing for microelectronics manufacturing. We're thrilled to have you all here and hope to provide you with an engaging and informative session this afternoon. First of all, let's take a quick look at what we have in store for you today. We're going to start out with epoxy application techniques. This is going to cover some of the most popular application methods for applying silver-filled epoxy systems. That includes screen printing, pin transfer, stamping, dispensing, and two-component dynamic mixing systems. Then we're going to go into a case study looking at the EPO-TEK H20E with the nano pen dispensing system. And then into an additional study where we look at several different EPO-TEK H20E variants and how that affects dispensing. Finally, we'll wrap up with a Q&A session. Bubbles, bursts, and dotting inconsistency can lead to low yields and ruined parts. The goal of our presentation today will be to investigate the leading industry trends in application techniques, how they apply to silver-filled conductive epoxy systems, before we deep dive into optimizing dispensing parameters for the highest repeatability and consistency. At Epoxy Technology, we find that adhesive application techniques break down into two major categories. That would be mass transfer and selective dispensing. Mass transfer, for example, would be something like screen printing, where larger quantities of adhesive are applied or moved at a time. They're in distinct patterns with very low variability to them. And that's compared to selective dispensing patterns. That would be like a syringe dispensing type application. That's going to be doing small dots or lines, other distinct patterns, but that can be varied over multiple products and is much less rigid than, for example, a screen printing application. Which segues us over to screen printing and stencil printing and the pros and cons associated with it. We see screen printing quite often. Screen printing is when you take the adhesive and you move it across a patterned screen or surface and leave behind a distinct pattern. This is a great method because it is fast, reliable, and can do a wide variety of dots. It also has some of the smallest dot capability of any of the application methods we'll be discussing today. That incredibly fine accuracy can make dots as small as 3 mil dots on a 5 mil pitch. That would be a 3 mil diameter with a 5 mil inner diameter to inner diameter pitch. The negatives of screen printing, though, is that it can have quite a bit of waste. You need a good wave of silver material to be going across that screen so that you can actually fill all those holes and make a distinct pattern. The screens also have to be replaced over time and cleaned occasionally. That leads to some situations where you might have certain screens being cleaned ultrasonically or something else, while the same pattern screen is also being used on a machine. Now, every single design that you have also has to have a different screen. Each one has its distinct own pattern to it. And finally, the material that you're applying needs to be applied onto a substrate that is quite flat. You can't have a lot of components on it. The screen needs to sit pretty snugly to the actual substrate in order to get a good repeatable pattern. Screen printing has a long history, originally coming from China as far back as the Song Dynasty. It was later adopted by countries like Japan and then transferred to the West, where it is now utilized in many electronic style applications, including the mounting of surface mount devices. This is typically done in a batch process because of the distinct pattern of the screen itself. And the thickness that you're commonly applying is about 2 to 10 mil. And that thickness is typically set by the mesh of the screen itself. Here you can see an example of the extremely small dots that are possible with screen and stencil printing. These dots go as small as 75 micron, or 3 mil, which is almost 4 times smaller than the smallest dots we recommend with syringe dispensing. This set of dots was produced with a stencil print, which is a little bit different than the standard screen print. With the stencil print, instead of a mesh-filled screen, you're using a negative cutout, almost like a street artist with a multi-layer stencil. A common example would be Banksy. Screen printing, on the other hand, uses a fine mesh filled with an emulsion. The emulsion blocks off the majority of the screen, allowing silver to pass through open holes and make its distinct pattern. This is the same process used in silkscreening t-shirts, for example. Next, we have pin transfer, which is a method of dipping a complicated tool into a reservoir of liquid adhesive and applying a distinct pattern to a substrate. This is great because it is fast, consistent, and can make very small dots, nearly as small as the screen printing method. The issue here is the material has to be pretty well developed for the stamping process. You don't want to have anything with solvent that could potentially dry out. Additionally, each stamping tool is made for one distinct pattern. Very similar to the screen printing, each tool and each pattern does one thing, one pattern, one product. Stamping is just what it sounds like. Stamping applies a given pattern of adhesive onto a part with something like a rubber or silicone pad. Stamping is a great method for low variability, highly patterned products. This could be stamping a logo, the pattern for an RFID tag, or silver traces using silver ink, for example. The stamping process is high speed and can cover large areas, but similar to screen printing, is typically done on fairly flat substrates. The silicone pads themselves can wear over time and eventually degrade. When that happens, the pattern that is being applied will be less crisp and will start to stick to the pad itself. Additionally, the adhesive used in stamping needs to have just the right physical properties. It can't dry out too quickly. If you have a highly solvent-filled epoxy system, there's a high probability that the pattern will dry out on the pad and not properly transfer to the substrate itself. Now we're on to what I consider the most common silver-filled application dispensing method, and that is time pressure dispensing. That is to apply a pressure onto a syringe full of adhesive and to allow it to flow for a given time into small dots, for example. These systems are easy to install. They have pretty low maintenance overall, commonly operated by a foot pedal, for example. You can get pre-mixed and frozen syringes directly from many manufacturers, including Epoxy Technology. They are generally pretty small pieces of equipment with lower overall cost. Some of the drawbacks, though, is they don't have as small a dot size as some of the other methods that we've talked about so far, like screen printing or pin transfer. The dot size you're typically going to see for dispensing is closer to 10 to 15 mils. They're also sensitive to bubbles in the syringes. So if you do have things like air trapped in the syringe from mixing, for example, that could lead to bubbles and bursts where you have small silver particles that are agglomerating in your needle tip and force you to change the pressure of the system, ultimately leading to misses in your dotting. Cartridge dispensing utilizes specialty side-by-side dual cartridge syringe barrels. These are Part A and Part B separated in a single cartridge that is dispensed through a helical mixing tube utilizing a cartridge dispensing gun. Because the A and B are separate, these are room temperature storable versus the single component pre-mixed and frozen syringes, which ship on dry ice and need negative 40°C specialty storage. These cartridge dispensing systems are fairly simple, similar to a caulking gun. The helical mixing tubes are disposable and relatively cheap, making cartridge dispensing very accessible, a low overall investment, but with less accuracy in the mix ratio of the epoxy and also lower dispensing accuracy because this is typically done by hand. Epoxies Etc., our sister company in the Meridian Adhesives Electronics Group, offers a wide array of cartridges and side-by-side dual barrel syringe systems with their Trigger Bond line. Volumetric dispensing or auger dispensing is very similar to the time pressure systems. This is dispensing a given volume of epoxy adhesive via an auger screw, piston, or gear pump. They're slightly more accurate than your time pressure systems. They can also give a wider array of dot sizes. They are typically designed to be fairly low shear, so they have low viscosity impact on the adhesive itself. They can be a little tricky though, because They can be very difficult to clean. If you accidentally leave the epoxy in the system, in that auger screw over the weekend, for example, you're going to be chipping it out all day. They can be quite expensive, definitely more expensive than your time pressure-based systems. They're sensitive to air and sensitive to the adhesive being put through it. Abrasive adhesives, abrasive fillers like alumina, can actually strip the inside of the auger screw itself. On the left, you can see an example of an auger screw. It utilizes the pitch and depth of the screw itself to define the volume of the adhesive that it's dispensing. By moving forward, it dispenses the adhesive, and by twisting the screw back, it actually can utilize a suck back, essentially pulling up and cutting the dot so that it doesn't have a tail. This is also a little bit different than the piston systems. The pistons are instead using a stroke volume to set the given dispensing volume. Now that we've covered some of the inner workings of a volumetric dispenser, here are a pair of examples of it being utilized. Here you can see two high-speed placements of EPO-TEK H20E, our flagship silver-filled adhesive. You can see a variety of dot sizes, lines, and the speed at which precision auger dispensing can be utilized. Next, we have jet dispensing, where a stamping foot strikes a reservoir epoxy and propels small droplets of adhesive onto the substrate. This is a great process because it is both fast and very accurate. You can also dispense droplets of material on three-dimensional objects such as stacked die or substrates that already have surface mount devices attached to them, because you instead have the jetter hovering over the parts rather than a needle which might strike the side of a die and have difficulty getting into tight geometries. Unfortunately, this is one of the most expensive processes and pieces of equipment in the standard set of dispensing systems that we're covering today. With jetting systems, you commonly see small dot sizes in around the 300 micron range, or about 10 to 12 mils. These are non-contact dots that are delivered very quickly and accurately. You can see in the bottom picture an example of a stamping foot that is coming down and propelling small droplets of epoxy. In this video, you can see an example of a jetter at work. This particular jetting system is the Pico Dot jetting system by Nordson EFD. On the left side is a premixed and frozen single component syringe of H20E SLR, a version of H20E specifically designed for the solar industry. As the video zooms in, you can see tiny silver dots being rapidly deployed onto a solar ribbon. In this solar stringing application, they utilized small dots of silver adhesive rather than long lines. With the speed of repeatable dots they needed, jet dispensing was by far the best solution for this particular application. Two-component mixing systems are, instead of utilizing a single component premixed and frozen syringe, you have a system that utilizes a hopper of A and B separated. This can be a great solution for very short pot life materials where mixing the material, the A and B together, could actually leave you with only minutes of pot life of the material. In this case, you can mix it right in line. This is great for large volume potting or very reactive products that would otherwise basically not be a viable pre-mixed and frozen system. The static mixers, though, do tend to have a little bit more waste and a little bit less accuracy to them. Then the dynamic mixing systems can be quite expensive overall and very difficult to clean and maintain completely separate A and B systems. In two-component mixing systems, there is a large difference between a static mix system and a dynamic mixing system. At the top right, you can see a static mixing system. That is the tube that is attached to the two-component cartridge. That tube has little folds through it, which are basically mixing the material through pressure from the backside. The actual mixing element is not moving. Versus the dynamic mixing system, which has an A and a B component dispensed into a central chamber, and then that chamber actually whirls and mixes the A and B together and then dispenses the material out into a cartridge or directly onto your substrate. In the video, you can see a static mixing system mixing the EPO-TEK H20E SLR that is utilizing one of the helical mixing tubes to mix the A and B together, and you can see it dispensing bubble-free, void-free, straight lines, great in this case for solar ribbon attachments. And that wraps up the Common Application Methods section of the webinar. Now, onto some practical examples of silver-filled adhesives being utilized with dispensing equipment. These studies were provided by the Pacific Adhesives and Pacific Equipment team in Asia, as well as equipment from the Epoxy Technology Europe team, both of which are now part of the Meridian Adhesives Electronics Division Group. This first study looks at H20E dotting repeatability with the Nano Pen dispensing system. For this first study, we look at H20E dispensed dot size over time while utilizing the Nano Pen dispensing system, the NPC3 by Teha. This dispensing system is a foot pedal operated time pressure dispenser. It utilizes pre-mixed and frozen syringes, which are single component versions of EPO-TEK adhesives, which we mix, weigh, freeze, and ship on dry ice all over the world. In this case, it was a 3 cc of the H20E silver-filled epoxy. Our goal in this study was to produce 400 silver-filled H20E dots with nearly identical size to make sure we were getting the most repeatable, consistent dots. We utilized a stainless steel tapered tip needle. That was a 23 gauge. The type of needle tip is critical for dotting repeatability. The common chamfered needle types tend to allow silver to build up or agglomerate in the needle tip. When silver agglomerates, it tends to back up the syringe, decreasing dot size, and eventually leading to bubbles or bursts. For this particular study, we also used a 3-axis desktop dispensing robot with the NanoPen 3 system and the NanoPen 10, the NPC EPO-10 control system. Our first set of results showed fairly consistent dotting, but a decrease in dot size over time. You can see in the graph 20 sets of dots dispensed, making 400 total dots. Though the size was consistent at about 400 micron, or about 16 mil, you can note at the end a distinct decrease in size. At first we suspected this was due to silver agglomerating in the needle tip. Now that can happen not only because of needle type, but also from high back pressure. We typically suggest low pressure of only about 15 psi during dispensing applications. Given our results, we repeated the testing with a nearly identical setup, same epoxy, same settings, needle tip, the main difference being a decrease in the back pressure. With time pressure dispensing systems, the back pressure is a critical factor, and we typically advise customers use a surprisingly low back pressure. The lower the pressure, the lower chance of silver agglomerating in the needle tip. If silver starts to agglomerate and back up the needle, that can lead to smaller dot sizes, bubbles, or bursts, which may look like a dot skip. We find that customers tend to increase back pressure when they start to lose dot size, and that can actually make the problem worse. More often, changing the needle or cleaning the needle tip to remove any potential blockage is the best way to get back to consistent dot size. In this case, the results showed the opposite. Instead of dot size decreasing over time, dot size increased over our 400 dot experiment, going from around a 400 micron dot up to a 600 micron dot. This didn't fit our previous hypothesis. Many of the factors like needle tip clogging, back pressure, or even material aging all led to smaller dots over time. This showed us that there was some other factor at work, and so we did a deep dive on the substrate itself. Though the dot size was quite consistent through our experimentation, on closer examination of the substrate, in this case PMMA, we noticed that our test parts were not completely flat. And in this case, the curvature of the parts actually matched up perfectly with where dots became inconsistent. In this case, we found even with optimized dispensing parameters, small factors like flatness of the substrate, the dispensing pressure, the needle tip, all had significant impact on dotting repeatability of the same silver-filled epoxy with the same dispensing system. Our second case study was to show how similar variants of epoxy adhesive could require significant variations in their dispensing parameters. In this case, we looked at H20E, H20E-D, the optimized for dispensing version of H20E, and the H20E-HC, the high thermal conductivity version of H20E. The H20E-HC boasts a thermal conductivity of over 23 watts per meter Kelvin, but is thicker than the H20E and is notoriously difficult to dispense. For this study, we used a slightly different kind of volumetric dispensing system, the Pressifluid system by Poly Dispensing Systems. Though this system looks like a time pressure dispenser, it is a special, no air pressure, non-contact syringe dispensing system that utilizes magnetism. Unlike traditional time pressure dispensing systems, which use air to dispense and suck back small dots of adhesive, the Pressifluid system utilizes magnetism for dispensing. A stepper motor applies magnetic force to a special metal attachment in the piston. The piston then compresses the adhesive in the syringe and dispenses repeatable small dots of epoxy. A magnetic dispensing system like this allows for not only precise volumetric dispensing volumes, but for equally precise backsteps, which are critical for forming hemispherical dots and preventing dot-to-dot tailing. This can be critical because in many cases, electrical connections need to be isolated to a single dot, and tailing from dot to dot could result in shorts that ruin an entire module. For this study, dispensing was done with a 3-axis dispensing robot. To the robot, we mounted a camera, which we used to examine dot quality. This type of demonstration setup is a service provided by Epoxy Technology Europe, as well as Pacific Equipment, to help our customers optimize even tricky to dispense adhesives. All 3 silver-filled products were tested with the same dispensing volume, dispense rate, and line speed. The main difference to look at here is the required backstep. H20E was able to make repeatable dots of a consistent size with almost no tailing. The line dispensing showed a little bit of accumulation at the edges of the lines, but in this case were quite clean, only needing a 150 backstep setting. After that, we investigated the H20E-D, the optimized dispensing version of H20E, again with the same dispensing volume, rate, and speed, but here far less backstep was required. The material was easier to control, its viscosity seemed very consistent throughout the trial, no dripping or tailing was observed. In the line drawing section, no bubbles or breaks were observed. The dotting experiment showed some of the most uniform and accurate dots, as well as allowing for the smallest gap distance in any of our trials. Our results truly showed why the H20E-D is our best material for syringe dispensing. Finally, over to the H20E-HC, the high thermal conductivity version of H20E. It is a much thicker, higher viscosity epoxy system, partially due to its higher silver content. So here, the same dispensing parameters were utilized, except for a larger backstep was required. Even with that larger backstep, there was still clear clogging in the needle tip, and many of the dots formed a little tail, a small hat, if you will. You can see in the lines tailing, and again, evidence in the top right corner that the silver-filled adhesive was forming a string-like material coming out of it. This kind of tailing can be a serious issue with small dot dispensing and potentially causing shorts within a system. And in conclusion, there were a wide variety of methods to apply epoxy in a microelectronics or electronics application. Mass transfer or selective dotting depends on the application. Screen printing is great for repeatable patterns on flat surfaces. Pin transfer can do repeated, high-precision pattern dispensing, though you have to be careful about the epoxy drying out. Dispensing, such as time pressure dispensing, is one of the most consistent and common ways to apply epoxy. But two-component dispensing is also used. When it comes to dispensing silver-filled conductive adhesives, a wide array of parameters lead to repeatable dots. Substrate flatness, needle type, and back pressure can all have an effect on dot repeatability. And even with similar epoxy variants, dispensing parameters need to be optimized. In the case of H20E versus H20E-D versus H20E-HC, the amount of backstep was critical to getting repeatable small dots of epoxy. Overall, optimized dispensing is about selecting the right dispensing process, the right application process, the right parameters, and the right glue for the job. Thank you, everyone, for your time and consideration this afternoon.
Thank you so much for that great presentation. And now let's get to the Q&A. We have some questions that have come in from the attendees, so we're going to move into answering those right now. If we don't get to your question, don't worry, we will have an answer for you following the webinar. Now for our first question. I am in the semiconductor field and have been looking for a die-attach material. We're about to convert to automated dispensing. What's the best product for me? Brian?
That's a great question. The best product for you will depend quite a bit on what application technique you end up deciding on. We have different epoxies for almost every one of the different techniques that we covered today. For screen printing, we have the H20E-PFC. For stamping and pin transfer, the H20S. And for dispensing style applications, the H20E or the H20E-D. For an automated dispensing application, I would typically consider that something like a time pressure dispenser or jetter style application. I would typically go with the H20E-D.
Great, thank you for that. Okay, now for our next question. How do needle tips affect the dispensing process?
Another great question. We have an entire tech tip, our tech tip 10, that goes over many of the needle tip parameters that we like to focus on or recommend. The first is the type of tip. That's tapered versus a chamfered versus an oval tip versus an angled tip. We prefer the tapered style tips. These have a very smooth inner wall that has much less potential for compacting silver, causing agglomerations, skips, and bubbles. The most common is probably the chamfered style. Those are, again, excellent options, but there is a potential kind of place where silver flakes can agglomerate in the base of the needle well into the tip of that needle. It can almost form like a little beaver dam. And actually cause a separation of some of the large silver flakes from the smaller silver flakes in resin. The angled tips also, that angle in the tip itself, that bend, can cause a lot of stress and require higher dispensing pressures, causing agglomerations. So for all of those reasons, we really prefer the tapered tips. In terms of needle gauge, we usually recommend a larger than 27 gauge needle, 27 being the smallest we typically see. Larger is usually very easy, 23, 20, anything like that, depending on your dot size. Finally, the pistons that are used. There's the white, the self-wiping, the orange, the free-floating, and the tan, the partial wiping. Overall, we tend to go with the free-floating orange, but I have many customers that prefer the tan or white color, and we'll offer any of those in our syringes.
Great, thank you. Okay, next question. How long does it take to thaw a syringe, and, if not fully thawed, what is the risk?
Thaw times for the premixed and frozen syringes will vary depending on the syringe size. So a 1 cc up to a 3 cc will thaw in about 15 minutes. 5 cc, we suggest about a 30-minute thaw time. 10 cc or larger can take anywhere from 40 to 60 minutes. We typically suggest taking a syringe out of the freezer and putting it into a test tube rack to cool and come to room temperature. We typically will suggest that because we don't want excess heat added into the system from hands, for example, or putting it into a pocket. That can cause freeze thaw voiding, cracking, and other issues in the syringe. So if you try to thaw it too quickly, you can end up with bubbles in the system. If it's not completely thawed, you're going to still have basically a pellet of epoxy stuck in the syringe and really be unable to dispense it. You won't get homogeneous dots.
Great, thank you for that. And to the audience, we are in the Q&A session. You can still send us your question by adding that information to the Q&A box on your screen and click Submit. As mentioned, we're going to try to get to everybody's questions. However, if we don't get to your question for whatever reason, we will reach out after the webinar is over. Okay, here is our next question. Is there an advantage of using one dispensing process over the other?
Really, all of the application and dispensing processes have their own distinct advantages. Depending on your part, your design will really tell you which one is advantageous for your process. Unfortunately, it's not a one-size-fits-all. Dispensing gives a lot of flexibility, time pressure dispensing or jetting. Screen printing gives a lot of speed, gives some very small dots, but has to be on a flat substrate. Pin transfer is also very, very quick, but again has to be in a fairly distinct pattern. And so depending on how many products you're making, how repeatable the pattern is that you have to apply onto your parts, and how flat your parts are, that'll really dictate which application method has the most advantage to you.
Great, thank you. Okay, next question. How do dispensing parameters change with high thermal conductivity systems?
Thermally conductive epoxy systems can be a little trickier to dispense. The H20EHC was one such high thermal conductivity material. And because they typically have fairly high silver loading and higher overall viscosity, they tend to be just a little tricky sometimes in terms of optimizing their dispensing parameters. In that case, I would actually recommend a different high thermal conductivity material if you're trending towards dispensing, and that is the EK1000 and the EK1000-1-D. Those are materials that have a little bit lower viscosity, have an equally high, if not higher, thermal conductivity, but have actually been specifically optimized for syringe dispensing style applications.
Thank you for that. Okay, now for our next question. How does epoxy dispensing contribute to the overall quality and reliability of microelectronics devices in today's highly competitive market?
Well, epoxy dispensing contributes to quality through repeatability. If you can get repeatable dots of the same size over and over again through your dispensing, through your entire shift, you're going to have great strength, great conductivity, consistent physical properties, and just the right amount of material that can flow around things like die or capacitors and resistors, what we call a fillet around a material. That three-dimensionality to a bond adds immense extra strength, much more than a purely flat bond can. So having optimized dispensing means you're not only going to get consistent physical properties, but you're going to get a high reliability of materials that you're overall not going to get with small dots or misses, skips, other things where you might not get the full robust dot that's really adhering your part.
Great, thank you for that. Okay, now here is our last question, but as mentioned, if we didn't get to your question, we will reach out after the webinar is over. Could you share some insights into the common defects or issues that can arise from improper epoxy dispensing in microelectronics manufacturing, and how can these be mitigated or prevented?
I've seen several ways of preventing and investigating defects. One of the most common that I've seen is actually something we utilized in our testing. That is the use of like a camera, like the CCD camera. The others that I've seen, some dispensing systems have microbalances incorporated into them. That is something that's actually taking a weight of each dot that's being applied. But really, one of the best mitigation techniques is knowing how to optimize the dispensing parameters, the needle tip, the back pressure, and having the right epoxy for the job.
Okay, thank you. And that was our last question, so we are going to wrap things up right there. So Brian, thank you so much for taking the time to be with all of us today. And of course, thank you for taking the time to answer some questions from the audience. And we would like to thank our audience members as well for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.